Now, okay. Hello, Fab Academy and FabLab Network. We are again in the Fab Academy Recitations. Today, we're going to have a really impressive talk about large-scale rapid prototyping and manufacturing with James Coleman. Thank you, James, for joining. The world is yours.
All right, great. So everybody can see the presentation okay?
Yeah.
All right, great. So we're going to talk a little bit about large-scale digital fabrication. And I work for a company called Zahner Company, which we do basically architectural one-offs. So we do great big projects that are of complex geometry and made of sheet metal typically, because we are historically a sheet metal company. So the agenda for today is we'll talk quickly about who we are, the kind of work we do, and then I sort of split it off into two different categories here. One that I'm calling the structured parametric design to fabrication, and we're going to talk about one project there, and then what I'm calling freeform parametric design, and then that'll lead to some of the more larger scale research trajectories that we have here. So if you get online and you go to Zahner's website, you'll see something like this. So Zahner does large-scale custom projects. What we're seeing here is actually the exterior of our building and our shop space. And we've done projects all over the place. There's probably not quite as many countries covered as the FabLab network, but we're doing our best here. And we have a lot of projects in the States, and then we're scattered around globally as well. And we're going to start with one of the projects that is sort of foundational for Zahner, which is the Experience Music project by Frank Gehry, and this is in Seattle. And what this project is a series of these very complex volumes clad in different types of metal finishes. As you'll notice, these are not your typical buildings. So this is sort of the wheelhouse of Zahner, where if someone has a project that is extremely difficult geometry or custom geometry, that we get involved. And we manage everything from the, let's make sure this works. Did everybody track with my link here, or are we still seeing the PDF?
We're in the PDF yet, still.
Okay, let me switch the screen I'm sharing.
Sorry, Tomas, there's background noise from your side. Can you mute when you're not talking?
I am mute.
Oh, then James, is that from your side?
Yeah.
Is there a little bit of background noise now?
Yeah, one of you has just conversation in the background.
Yeah, I've got some coworkers here, so we'll have a little bit of background noise. Can everybody see now the Google Street View?
Yep.
All right, great. So we're going to pop around and take some tours. So here we've got the Experience Music project, which you can see here. This is the side that has what we call angel hair stainless steel, which is the silver section. There's many different types of material. And so with this project, this happened in 2000, and although Zahner is a fourth generation company, this was one of the first projects that was of such a complex nature. They required a lot of very interesting and early on techniques in computational design and sort of geometry rationalization. So you can imagine underneath this skin is a complex network of ribs and structure that define the geometry, and then knowing the material constraints, we can actually start to shape and manipulate the metal on the top surface. So this was in 2000, and this was sort of wasn't quite the beginning of Zahner's digital fabrication entrance. That would have been in the late 1980s when Bill Zahner purchased our first CNC punch. But this was one of the first times where we really had to dive into the computational side, and through that, we're going to talk a little bit about the types of software we use, and for that project we use ProEngineer, and it sort of led us into using CATIA as our base platform. But what is the sort of difference between the kind of fabrication we do and the fabrication that happens in the Fab Labs? You'll see on the screen now. You'll see this little diagram where in the Fab Labs you typically start on the computer. You do some designing in some sort of CAD software or online in the Fab modules. And then you actually head to the CAM software, and then you end up sending your files to the machine. And while we know this quote well from Neil, that this is great for a market of one person, in a similar sense, at Zahner, we do sort of one-off architectural projects. So digital fabrication really helps us deal with the massive complexity of all these unique parts and giving us really precise parts. And because architectural projects, especially the kind that we get involved in, there's only one. We only do one of those projects, and then we have to move on to the next one. So unlike companies that do tens of thousands of unique parts, architectural projects have a lot of variations in the site and in the use. So we don't have the sort of convenience of making the same thing twice. So in a similar sense, we do very similar workflow that the Fab Labs do, but instead of the machines being the size of a person or a desktop, some of our machines get quite large. But we still follow a very similar trajectory of designing the computer using, I've got a sort of robust CAD, because once you start dealing with tens of thousands of unique parts, you start to break down with some of the softwares. Even my preferred software, Rhino, just has a really hard time keeping up with that many unique parts and organizing them and making sure that tolerances and things of that nature match. And having a look inside, the way we typically work is we take a building project and we do everything prefab. So we split it into component parts, and then we build those parts in our factory here, and then we have to ship those parts to the site. And so what we're seeing here are these large parts that are about 9 feet by 6 feet by 40 feet long. And these guys are all pre-cut in our shop using water jets and CNC punches and other tools of that nature. And then they're pre-assembled, pre-clad oftentimes, with infrastructure. And in this photo you're seeing that there's even some glazing that has been added in. A lot of the internal systems are accounted for, which you can see on the left-hand side. There's holes and things passing through all these different ribs to account for all the various infrastructures of the building. And so we coordinate a lot with different trades and crafts to be able to do the prefab and then ship these massive parts on site. The guts of these things are basically these section curves of these really complex surfaces that act as that skeleton I was telling you about before. So you can imagine the museum we were looking at earlier. Underneath that skin is things like this. So let's move on here. So breaking down this a little bit further, everything starts from this large computer model. Remodel everything down to the nuts and bolts that do the final connections, and then we tag them, we organize them, and then we ship those parts to our fabrication machines. This project we're looking at here is Zaha Hadid's Road Museum. We can zoom over there. So this project is in Michigan State. You can notice here it's a series of less curvilinear parts, but still very complex, and each one sort of cantilevering out, and so there's a large amount of engineering that happens prior to our fabrication process, and then these parts are shipped on site and assembled into these great buildings. And so this one here, you can see has a very different type of structure, but it's a similar concept where we break the building down into component parts, and then we stitch them together on site. So this is at Michigan State. You can sort of see the entrance here, like so. So how do we do these projects? So the first one we're going to talk about is a museum in Los Angeles. And so we start with something like this, which is the architectural inspiration. This was a rendering done by KPF, showing the larger surface that they hope to achieve. And this project was a large building that existed, and we came in and we wrapped it with this custom skin. And so KPF starts with something like so. You can sort of see the process here of wrapping it. And this is when we start to get involved. So the architect has lots of tools these days to make very interesting and tricky to build surfaces. So then our first thing that we do during a period we call design assist is we start to break that down into the manufacturable sections. So here you're seeing our CATIA model with the sort of ribbons now sliced and broken into component parts. And oftentimes the parts are limited by just what we can ship. So a typical tractor trailer in the United States, we can ship things that are about 9 feet by 40 feet fairly easily without having to have any exports. So oftentimes you'll notice that the buildings are actually composed of parts that are about the size of a truckload. And so zooming in here, we have a look at these complex ribbons. And what we do is we start to break them down and get closer and closer and closer. into what each of the component parts are made of. So here we see in the green the skins, which was stainless steel, and then the interior we have these aluminum fins that we cut. So during the design assist process, we break these down and we make prototypes of them. So what you're seeing here is a structural tube that is in the center of the surfaces, and then those ribs that are cut and do the shaping of the ribs or of the skin, and then the skin added. And then we do these large-scale mock-ups. And so this was the mock-up for this project, and it's a proof of concept, but also a good way for us to test the manufacturing process that we've designed for that project. Once we have a successful prototype, we can use that logic and deploy it over the rest of the project. So we do a lot of parametric design in CATIA, and what we can do here is we can share that logic between different models. So we take what we see here, and all the logic is sort of represented in this image, where everything down to even the stands that hold up the fins as we are fabricating it are generated, as well as the shipping mounts, which are on the edges here, so that we can easily lift them and carry them around. And so all this is generated from basically the white lines on the interior here. So we start with those white lines, and then we basically place in our structural tubes. We cut those tubes and we create these custom boots. And this is all happening. This is all automated. So once we set the logic for one, it works for all of them. And so then the structural boots are attached. All the fins are placed based on those bounding surfaces. The cross supports of the substructure here, and then the skin is finally rationalized and split into manufacturable sections. What's nice about this process is that our construction documents are also generated. And so although at Zahner we have sort of a diverse set of construction documents that range from actual 3D models we send to the shop to typical 2D drawings, we sort of can pull extract all that information right out of our models. Seen here some of the metrics and some of the labeling conventions of how we define these wild surfaces. And then we do things like this too, where we study how we might organize all these parts. And so what you're seeing here is in these blue volumes is actually a truck bed, and so we can do some optimization of how we pack these guys together and how we can efficiently and effectively ship all of our parts on site. So just like we saw in the previous image, now we see all of our parts nested basically in these truck beds and ready for shipment. You'll notice here that all of the upstands that basically give us the ability to stand them up when they're not actually in place are all generated at the same time. And then we're brought on site and lifted into place. And then there's some really interesting things that happen as far as the quality control, because it's all good and fine to design these things on the computer, but oftentimes steel tolerances and errors in the construction process can throw things off. So the idealized world of the computer model can oftentimes be harshly associated with the actual on-site construction. And so we provide tolerance for these things where we can move in a sphere of up to a couple inches to deal with any sort of errors in the constructability of the other trades we're interacting with. We typically work to a 30-second tolerance on our projects, and the typical construction tolerance in the United States, at least, is up to an inch in a sphere, so it can be in any one of those directions. So oftentimes our anchors are some of the more interesting parts, where it allows adjustability in yaw, pitch, and roll, but also in X, Y, and Z. This building was completed. This is not quite a completed photo, but now you see all the ribbons put into place, and that the only on-site construction that happened was basically the finished skinning of these seams here. And if we zoom back here real quick, when Google updates their Street View, we could take a tour of it, but now you'll see sort of behind the scenes look at that process. So here you can see there's a few of the skins put in place here, raised up, and we also did the sort of red corrugation on the backside, which was funny because corrugated metal is sort of a ubiquitous material, but In this project, the architects had specified no taper on them, so these are actually custom broke form corrugated metal that we did for them. And so we'll see when this is updated, but this is what there's before we started. So let's see back here. So that process you could see is really great once you know exactly what you want to do. You can set all these parameters, and then it is a really robust CAD platform that allows us to do things like the Peterson Automotive Museum. But it is a very rigid way of modeling. So it's I find it in a lot of ways pretty limiting. Well, here is also a video of the construction process. So now you get a little view into our shop here, where because we only do one of each project, we don't have long assembly lines and permanent infrastructure. Everything in our shop is on wheels, and we have these large open spaces and lots of cranes, so that we can move things around very quickly and adapt our production process. And so now we're seeing all the culmination of all the fabricated parts. So the water jet fins here in the center being assembled, the punch skins, where the holes and the countersinks and everything are already placed into all of the skins, and then they're hoisted up, placed on their carriers, and shipped onto a truck. All right, so that is what I'm calling the sort of structured parametric modeling, where we have very explicit rules. We use a software that is designed for making assemblies to make assemblies, and then we take it through the production process. And there's lots of interesting things that happen in there. And there's also a lot of accumulated knowledge. And so the second part of the structured parametric design I want to tell you guys about is something that we call Shop Floor, which is a web design player that we've generated that allows people to basically utilize a lot of that accumulated knowledge from these projects and design their own projects. So I'm going to shift over here real quick. So if you go to Zahner's website, you'll see here on the top there's a tab for Shop Floor. If we click on Shop Floor, let's see here. We've got a few different products that you can design online, and then basically get a real-time cost estimate for that project. And so what we're doing here is we're taking a lot of that accumulated knowledge that comes from doing projects like Peterson Automotive, and encapsulating that into a web player so that other people can start to manipulate it. So this is a full 3D modeling environment where you can upload an image, and then you can manipulate that in perforated metal facades. So you see you can adjust the hole sizes. We can, what else can we do here? We can play around with different gradients and reductions. And if I'm not currently logged in, but typically in this upper right-hand corner you'd have a real-time price for exactly what that project was going to cost to manufacture. And so we can do this because we've done a number of these, starting with the DeYoung Museum in San Francisco of perforated metal facades. We have a very good idea about how they go together, what the costs of those are, and so in some sense it's custom, but it's it's sort of curated by us, and so that we can make it manufacturable. And then we have a number of different materials we can play with. We can put it on black painted material. We can do it on different anodized materials. We could put it on quartet steel. And so what this becomes is sort of a, let's shift out of here. And there's another one we want to look at real quickly. So this is a way for us to sort of share some of the accumulated knowledge that we have, and also help people do projects that aren't quite the scale of a whole museum, which has been an ambition of ours, is to help do projects that don't have to have a gigantic budget and whatnot. Another one of these platforms we have is is what we call bench. And so what we can do is we can stretch and we can manipulate this bench. And see an update here. And so you can manipulate this guy, and we capture a lot of the knowledge we've generated in the production of this bench designed by some Zahner colleagues of mine. And in a similar sense, we sort of give this structured parametric model to the user, and not unlike what we would do with an architect, one of our clients. And then when you're ready to, you have a bench you like, you can hit print, and we'll make it for you and ship it your way. So anybody's free to get on here and play around with these and save your drafts and whatnot. And so that's the sort of end of the structured parametric design. Let's go back here. Use that image wall player so you get to. So the next one we'll look at is a project that's ongoing, and this project is happening in New York City, and this is for Cornell Tech, and it's on Roosevelt Island. What this project is a series of panels that have these small louvers that are all rotated both in plane, but then also we sort of roll along an axis of that plane. And so you'll notice that depending on the direction they're rotated, they either light up or they sort of darken and they're in shadow. And then throughout the day, as the sun passes from east to west, it sort of inverts. And so you get this really dynamic facade. And this project is designed by Morphosis and Tom Main's group. See how that goes together with the various panels. And the reason I'm talking about this project is this is a manufacturing process that is very different than the previous projects, where we need something to be able to manipulate all these various tabs. And the project itself is, you see here in this top left corner, there's, I think we have now shipped, I think, around 2,500 of these panels, each one having 125 unique rotated tabs. And so everything here you see in the purple is those panels with those rotated tabs. And so there isn't really a well-defined process for doing things of this nature. So, there isn't a CATIA button that says, rotate tabs or generate, machine code for a machine that could rotate these tabs, because the machine doesn't really exist. And so what we do here is we're actually using Rhino and Grasshopper to do what I'm sort of calling the freeform parametric modeling. And what's nice about Grasshopper is that you can manipulate geometry in a similar fashion as CATIA, but we can also do things that are absolutely have nothing to do with geometry. And that's exactly what we're doing here. Is we're basically taking in the input from the architect, which was a series of images that they wanted to portray through the rotation of those tabs. So we basically do a sampling, not unlike the fab modules of that image, and we find the darker places and the lighter places, and the darker portions we rotate the tabs more, and the lighter places we rotate them less. And so what we do here is we take those rotated metrics and we feed them into Grasshopper, and we generate robot code to go through and rotate each of those tabs. And so along with that, we also automate the ticket creation and the tool pathing for both the robot and our CNC punch. So we do we generate DXFs, which you're seeing here, for the punch, and then we generate robot code for actually controlling the robot. What that process looks like. Is something like this. Where once we've shipped the DXFs to the punch hits these little half moon shapes into the material at the appropriate angle for how we're going to rotate it, and then we key that in with the robot so that the robot can come and can compress each of the tabs to the exact angle. So you can imagine that this is removing the burden of trying to do this by hand, which would both be extremely tedious but also difficult to calibrate each of these various angles. And so we can now send different depths to the robot and do all the different rotations for creating that image for the facade. And so in this way, we we don't have to sort of follow any sort of rules like CATIA has for us. We can generate everything from the geometry to the fabrication files to the code for anything. And what that leads to is some of our larger research goals, which is how do we create custom machine processes for these different projects. Because oftentimes the first thing we do when we get a new machine is we start to push its limits, because an architect comes with an idea and we say, okay, well, can we do that, and how can we figure out how to do these different types of processes? And so we manipulate things like the robot, or we've had a punch for over 30 years now, and so we do things with punches that the punch designers had never ever considered. So how do we sort of capture that mentality and formalize it into creating of custom machines? And the purpose for this is A, to expand our capabilities, but also to remove some of the headache of interacting with third-party machines. So I'm sure you guys have seen and working in the Fab Labs that each machine has its own set of difficulties, right, and strict processes, which many are removed by dealing with the Fab modules. You don't have to learn 12 different cams for the 12 different machines. But we are constantly running into this problem where we have a very robust modeler, which is oftentimes CATIA, and then we have to sort of do a lot of conversions from taking those and breaking them down into lines, for instance, into like DXFs, and then converting those DXFs, based on what the machine can read. Oftentimes, if you give it a spline to some of these older machines, the machine doesn't understand what you're trying to do, or it provides far too much information to the machine, and they have limited processing power, so then they crash, and so it's sort of this roundabout situation where we can go through oftentimes up to 6 different softwares from our design to the actual running of the machine and the operation software. And so this costs us a lot of time, and also limits what we can do with it. We get away from that a little bit with similar to what you saw with the Cornell project, where we can use robots, and with a robot, we have one way of controlling it. If this is a KUKA gear, so we would send it a KRL code, and then depending on what we have on the end of it, the functionality can be changed. And so here we've got sort of a much more streamlined way of working with the machine, where we have one software and we can output one type of code. But robots are oftentimes a big headache to make work, and the kinematics can be a pain for different types of operations, and in many cases they're overkill. For instance, you imagine the Cornell projects could be easily turned by a 3-axis machine as opposed to a robot. We sort of have to mix and match our tools here to make it work. But this is where some of my interest in machine design comes in, and I know you guys have gone through the machine design process and hopefully had a lot of fun working with the cardboard kit that Nadia and I have worked on. And what's nice about this in the sense of Zahner, and also with Fab Labs, is if you can create your own custom processes, then you're not limited by what your tools can do, but you can generate the tools to per project. So you can imagine if an architect comes to us, or an artist comes with a complex project, oftentimes we have to say, okay, well we can't do that because our machine is only this big, or because our machine can only do this functionality. The reverse of that would be, okay, well, what kind of machine would it require to do that process? And the cardboard machines has been sort of a test bed for that, on how you can quickly make these different types of machines. And obviously we've seen lots of variations of the cardboard machines, and the goal now at Zahner is to scale that up. So similar to our earlier slide, now that we have to make thousands of parts, and oftentimes they're the size of a building, what would a modular set of equipment look like at Zahner? And when we can quickly change out the functionality of each of our bays in our factory to take on different types of projects and different types of processes, and really expand what we're able to do. And so I'm going to end here, but we'll be hopefully talking again soon about some of the projects that have come out of this, and we're doing some active research on metal forming and different types of kinematic models to shape metal, as well as automating our patina process to to give not only a patina but variations of each of those patinas.
So, James, let me jump in. That's beautiful work. Within that, talk about what you're doing individually. What's your arc? What's your current and future role?
So I'm a research and development engineer, and so we get involved in a lot of different ways. With each new project, there's new and different requirements that show up, and unfortunately that can sometimes lead to a lot of chaos. Because everybody is trying to scurry and figure out exactly how we're going to make each of these buildings, and with each new building, you can only predict so much, and so we sort of work in as a tactical team that go through and develop automation routines for sometimes for the releasing of files or for the example of the Cornell project, the full process development of how we would rotate each of those tabs and the configuration of the robot, and then the larger. So that's all sort of applied research. On the more basic research side of things, we're looking further ahead at some of the things we're seeing here on the screen, like the machine design, machine control, and purchasing the machines. And so I've been actively working in the acquisition of new machines, as well as the development of some of these machines. So looking into how we're both going to purchase, but also create machines in the future. And that's a lot of that is sourcing and dealing with where can we find platforms that are open and available for us to do our motion control, as well as interacting with other researchers, like in the case of the metal forming, and how we can integrate that.
Then a couple comments and questions. I'm not sure how much Nadia got to update you on the next spiral around on the rapid machine building is involving both data flow programming and hardware and modular programming and software to make it easier to compose workflows. And I really liked the kind of spiral of echoing that, in a warehouse-sized rapid machine building. I think it'd be great if, like, the quick tabletop prototyping led to the ability to do quick full-scale prototyping.
I don't think they're too dissimilar, and I think it's absolutely there. And what I really like about working at Zahner is that we're at a scale where we can invest in some larger tools, which is oftentimes why things remain small in a workshop type of environment. But we're also dealing with such a diverse set of projects that it requires such things. Most factories, if you went to IKEA and you said, actually, I want a table that is slightly smaller than your current table, they would say, well, we don't do that. But here, every one of our projects is so different that we will literally reconfigure or build a whole new building, to take on this project. So the scale of it is really exciting, and the agility of what we do here is a lot of fun.
To alert people, this is in Kansas City, Missouri. It's in the middle of the country where there's room.
That's true. That's true. Sometimes we have entire buildings spread out across our parking lot.
Then another comment is, it's interesting you're using CATIA. A number of the labs use SolidWorks, and SolidWorks is involving to merge its engine essentially with the CATIA engine for that kind of scalability.
Right. Well, we've just shifted into 3D Experience, which is Dassault's new sort of all-encompassing cloud-based modeling platform, and I think. Well, oftentimes I think that it is nice to have a robust company like Dassault backing the software, right. But it can also be so limiting. It's nice to also be the sort of quick and dirty version of Grasshopper and some of the more open source softwares.
So that was I was going to ask. Talk some more about other tools. Like, what do you use for rendering, for FEA, for path planning? Talk about some of the workflow tools.
Oh, okay. So for the rendering, we really don't do a whole lot of rendering. The architects normally are much better at that than we are. So they come with the beautiful renderings, and then we ask them for their sort of base surfaces. So oftentimes we're dealing with architects who bring us Rhino models that are just pure surfaces, and then we do a lot of gymnastics to convert those into cleaner surfaces and things that we can make. As far as path planning goes, that hits a little bit towards some of the frustration that I showed in this slide, which is each machine is very different. You know, controlling the water jet versus controlling the punch, you know, versus controlling the robot. But we are actively trying out a software called Sigma Nest, which is basically an all-in-one platform that allows for, it's almost like a Mastercam where we can host to many different types of machines. And so our goal there is to try and limit the number of softwares and the number of formats we have to work through. But unfortunately, you know, oftentimes Sigma Nest is okay at running tools, but not great at each tool, right? You know, there's nuances to the tools that you know, are not captured by some of these third-party softwares.
And then what about physical modeling?
So we don't have an in-house structural engineering firm, but we have a number of you know, sort of FEA softwares that we interact with. You know, some of them are actually housed in CATIA. You know, there's some plugins for doing CFD and structural analysis there, but oftentimes we outsource all of our structural engineering.
Okay.
And so,
and then do you get involved in material selection and development, or is that done by the architects?
now oftentimes architects have no idea what they want. You know, they say, you know, what is the best metal? Well, okay, well that sort of depends on what you are trying to do. So a lot of it is education of the types of metals that are available, and also what they do. And what you're seeing on the screen now is the De Young Museum, which was done in 2005. And you know, material has you know, metal has a life of its own once it's out in the elements. You'll see on the left side when the De Young was installed, and on the right side what De Young currently looks like. And you know, these metals will react in different environments in different ways, and so you know, we always have lots of fun conversations about, you know, what metals are available, you know, what would be the appropriate metal for the project, and also, you know, budgetary selections. But it can range from copper and stainless steel to, you know, we were recently talking to an artist who wanted to use titanium, and if you put titanium into a phosphoric acid solution and then you electrify it, you can actually turn it rainbow colored. And so we do a lot of wild things like that too, where, you know, if there's a reason for, you know, creating a custom material, and if we can do it at the scale of the project, then we'll pursue, you know, different patina processes and different material finishing processes.
Great. So again, it's really beautiful work, and I like how you made the connection to help see how what one person does in a fab lab isn't that far off from what like Zahner does on the scale of a Geary building. So I'll drop off and listen in, and Tomas, go ahead.
Yeah, well, thank you very much, James, for sharing your work. I think I will throw a question that probably gathers some of the feeling of the Fab Labs, which is what is the point in which you decide not to ship parts in containers and to manufacture locally? And what makes that decision? Is shipping cost? Is error or risk? How do you do that? I mean, when do you see that point, the tipping point in which you decide from shipping containers or shipping factories?
Well, the tricky part is, you know, we have several hundred years worth of experience here at Zahner. So many of our sheet metal workers have worked here for upwards of 20 to 30 years. And so it's tricky for us to hand off a lot of these projects because the tacit knowledge that's gathered by, you know, working with the material over this, you know, these many years is so much a part of our process. So we rely on their expertise. So we have a difficult time, you know, handing off a factory because, you know, just as you guys, you know, I'm sure have seen, you know, you can tell one of your friends in the Fab Lab how to make something, but when you walk through it with somebody and you have somebody who's done it before, it makes it much easier. So we've done it a few different ways when we are limited by shipping. We did a project in Qatar where we were limited to shipping in containers, but the parts were much bigger than containers. So what we did there is we fabricated everything, we put it together, then we took it apart. And then we created a very, very long set of instructions for how to reassemble these things. And then we sent a few of our engineers there that worked with the local craftsmen to reassemble. But you know, it's tricky to ship some of these tools and expertise. I mean, the punch press machine weighs 20,000 pounds, So short of you know, taking some of our workers and sending them to a remote location, we do mostly everything prefab, and we figure out ways to fit it into to that little whatever our shipping restriction is, that unit size.
Oh, thanks. Another question. You mentioned the IKEA, and it's funny because we're running in about a month a workshop with the IKEA team in our FabLab, and they're looking to change their business inside. They're looking to design or to change the patterns of design. It's something that or how they design. And somehow you show this customizable tool in which you say not even the architect, but actually the client can basically set up and design a bench or a facade and order it. How do you see that happening in a smaller scale, let's say, home retail or furniture scale? You see mini factories in the city, or do you think that it's still like as you do the parallel with keeping some things under control and experience, or we can give those away when the scale is smaller?
No, so I like that question very much, and that was actually my thesis topic, which was a housing tower that incorporated fabrication equipment. I think, and IKEA would be a very fun group to speak with that about. And what I think would be really interesting is how you tie together large-scale manufacturing with small-scale customization. So you can imagine if IKEA, instead of designing full units, they designed smart parts that were then shipped and then locally customized. So we'll never compete with the economies of scale that you can reach with people, groups like IKEA. But what we can do is we can customize, we can hack it, we can modify. So I absolutely see distributed manufacturing as a viable option, as long as it's paired with with the economies of scales that you can get from large scale manufacturing. So yeah, I think a lot of fab labs spread throughout cities or in the home is absolutely viable. But we're going to need different types of tools, because the tools now we're not going to have the tools that we have at Zahner here in your house, because they're too big, they're dangerous, and they're difficult to use, and they require a lot of expert knowledge. So pairing out the types of tools that could work in the home or in the city or in the community library, I think is key for that. Hopefully that answers that question.
Yeah, thank you. Yeah, absolutely. Probably we would love to have access to your thesis. If it's publicly accessible, it would be really great.
Yeah, no, it's online at MIT.
Okay.
Distributes theses, so you can get onto dspace.mit.edu, and I can send you the link. But all MIT theses are open to the public.
Awesome. Okay. So great. I think that the main questions have been covered. I don't know, Neil, if you want to add anything.
No, it's beautiful work, and I think it's inspiring for how small the gap is from what we're covering in Fab Academy to the largest scale of fabrication.
Yeah, absolutely. It's similar workflow, and collaborations between these groups could be a lot of fun. And
so maybe we can have you back next year, and you can present your machine building assignment. Warehouse-sized machine building assignment.
That sounds good. I'll look forward to that.
Okay, it's a date.
Okay.
Bye-bye, everyone.
Bye-bye. Thank you very much, James.
You're very welcome. Bye, everyone.
Bye.